we're trying to basically build the all-in-one 2D graphics editor for all sorts of graphic design, digital painting, illustration, um, page layout, kind of everything that you would use any sort of 2D software for. Most of those are the Adobe software such as Photoshop, Illustrator, InDesign. Someday even we'll do animation, so you might know of After Effects, and there's also a number of other animation tools from other companies as well. In the open source world, there's GIMP, there's Inkscape. So GIMP is a raster editor, Inkscape is a vector editor. And vector graphics, basically, you can think of it as like clip art or anything that is based upon just solid shapes, or maybe shapes with some subtle gradients applied. But they're not images that are generated with a camera, because those are encoded into pixels, and that's called raster. When you have pixels that make up an image, or when you're just drawing with a paintbrush, those are going to be built as pixels, whereas vector is more about those shapes that you can make illustrations with, or graphic design, or also like laying out text, because text is ultimately composed of curves. All of that is referred to as vector, whereas raster is anything that's based upon pixels. And at the moment, in the software market, whether that's open source or proprietary, all of those tools usually are segmented by just focused almost entirely on vector, or just focused almost entirely on raster. And then even within those categories, you have things such as like desktop publishing or page layout. If you're designing a pamphlet or a book or something that's going to go to print, and you need to put content such as text together with images and other sorts of content, that's typically going to be using a digital publishing application, so such as Adobe InDesign, and then there are some open source alternatives, but they probably aren't worth mentioning because no one uses them. They are
There's Scribus.
strictly inferior,
There's
unfortunately.
Scribus, for example, which is quite widely used, I think.
Yeah, but my understanding is that Scribus is not quite up to the task of most work in the industry, so people just always will use InDesign. But basically, it would be really good to have that built into another open source program that also lets you do the graphic design. So you don't have to do graphic design separately and then import it into your desktop publishing application. And then if you're doing any raster work, so anything that involves a photo or painting or complex effects that can't really be represented as mathematical curves, doing all that design in the same program that you're doing your page layout for if you're working on a book or a pamphlet or something. Having all of those tools in one program would be very useful. And at the moment, there's sort of this artificial segmentation in the market of different tools, whether that's, again, open source or those provided by Adobe or from others like Affinity Designer and Affinity Photo and Affinity Publisher, I believe, are the three different products that do mostly graphic design and vector stuff, mostly photo editing, and mostly desktop publishing. And then finally, animation is something that we'd like to eventually get to as well, because there are a bunch of different tools that do animation. They're mostly focused on that, but we would like to be able to have those as part of the same tool that you're already doing your 2D design. So if you're working on any kind of motion graphics video or something like that, or even just something very simple, but you want to do something that involves time, something that involves motion, that will require typically that you do your design, all the graphics themselves in a vector editor, and then move those over to your animation tool, import those, turn them into something that can be used and laid out in a scene, and then do your animation in that. And then if you ever have to make any changes to the design, to that actual artwork before it gets animated, you got to go back to your vector editor, make changes, and then go back to your tool. And that's actually a big reason that people really love the Adobe products, and why I love it, frankly, for that matter as well, is that even though they are separate tools, they at least have really good interoperability between them. You can double click on a layer in After Effects and open up the Illustrator file in Illustrator, and then make your changes and hit save, and it will automatically sync those changes back to After Effects. Same with if you're working in Photoshop on a document where you've imported something from Illustrator. Double click on that, brings you to Illustrator, make changes, save it, and it automatically syncs back to that. But the only thing better than having nice syncing between products is having one product that does all of the things. And then if that can be open source, that would be doubly awesome. So that's kind of the very ambitious goal, is to build all the 2D workflows into one program. And that's actually something that Blender has done very successfully. In the 3D world, there is modeling, there's sculpting, there's texturing, there's UV unwrapping, there's animation, there's weight painting, there's rigging, there's uh, I think I already said animation, but there is rendering, look development, shader development, and I'm sure there's a bunch more that I'm forgetting. But all of those are different things that you might, yeah, and oh yeah, compositing at the end. All of those are things that you might do in separate tools, or even in Blender's case, even taking your final videos and then compositing them together in an Elite editor, so you can combine the clips together and do video editing at the end with audio, adding audio tracks, adding video tracks together. All of those are built into Blender because they wanted to have the entire workflow under one roof, and that works really, really well for them because they don't quite have that interoperability problem, which other programs that only focus on a specific thing work on, because you just do it all in one program and you have a very, very seamless workflow. So that worked well for Blender. And the other thing that really worked well for Blender is that they were trying to work on not just trying to catch up to other tools, but they were actually innovating and bringing out brand new concepts that no tool had ever built before, such as a real-time viewport that displays your actual final render in real time. So you can actually work in the viewport and have that render as you work. So you know exactly what your render is going to look like as you build your scene. That was something that really no other software meaningfully did. Not part of the tools, at least. Not part of the tools you could use to model and sculpt and change your scene and build your shaders. And that's just one example out of dozens or maybe hundreds of things that Blender actually innovated with. So the way that they succeeded was actually to build something that is new and something that is compelling, not just something that is always trying to perpetually catch up to the others. So we're taking the same approach here is we want to bring things that are new and are innovative and are actually very exciting, not just simply try and catch up and copy all the other things that other people are doing. So in our case, what we're bringing to the table is the node graph. And I think I'll cover this in more detail later because I don't want to go too long on this one topic. But the node graph is very briefly a way of encoding all of your artwork, all of your creative decisions, everything you've done to build your project, to build your 2D art, encoding that not quite as data or curves, but not quite as pixels for raster or curves across various layers for vector, but instead you're encoding this as kind of like a program. You're encoding it as a big flowchart of functions, of operations that combine together in a node graph and build the thing that renders into your artwork. And then giving you a whole bunch of tools that you normally are used to in existing editors that instead of modifying pixels or modifying curves, they will modify that backend that encodes everything in a node graph, that encodes your artwork. Those tools are building the nodes for you and modifying the data that goes into those nodes. And then it renders in real time as you work with the existing tools that you're already used to and you're familiar with. But instead of being stored as pixels that are destructive, so destructive means that you are writing over one color of pixel with another color of pixel. And as soon as you're done making that change, you can't really go and say, I wanted a different color to write over that color, because you don't know what the original one was. You can't undo that operation. You can literally hit Control Z, but you can't come back half an hour later and decide, I wanted blue instead of green, or I wanted a blur that was 10 pixel radius instead of 5 pixel radius, or I wanted to have 5 flower petals on my flower instead of 3 flower petals on my flower, or I don't know, 50 instead of 30. Those kind of creative decisions, if you're storing them as data, that is something that allows you to come back and make meaningful creative decisions later, make changes to those creative decisions later down the road. And it allows you to iterate much faster as an artist. You can try many more things because you can say, does this flower look better with 50 or 30 petals? Or does this look better if I have a lot of blur or less blur? Or what color is actually best in this scenario? Those are things you just can't do in other programs. But with a node-based approach, where you're storing things as data instead of pixels, that is a significantly improved workflow. And that's what we're trying to build, something that is brand new to the entire industry.
I see. So, like, the way I think about it, not node editor is that you record the operations that the user does. So for example, take, I don't know, the pencil and draw it from in these points, and then, I don't know, apply this effect and so on and so on. And so when you save the file, for example, I imagine when I save the file in GIMP, maybe they only save the current pixels,
Exactly.
and so you cannot control Z. Instead, you store the whole operation that the user did. I see.
Yeah, because they're actually, to get a little more into the detail here, there actually are no such there is no such thing as pixels. As in, layers are not composed of this grid of pixels where you, at the beginning of your document, just at the beginning of creating a document, you decide, I want my document to be 1920 by 1080 pixels, and you're committed to that decision. And you can draw things on it, and maybe you decide, I want to double that resolution later, but if you double it later, you're just going to have to upscale whatever you worked on before that point. In our case, we don't have pixels. Pixels are something that happens when it gets rendered, which is to say, every time you ever make changes, every time you zoom in, we're going to re-render your document. And the render engine is going to pick how to render it at the current resolution you're viewing it at, or the current resolution that you're exporting a file. But there are no pixels that are set in stone because you're not operating on pixels. You're operating on data. And the resolution that you're viewing or the resolution you're exporting is just where we end up choosing to make pixels show up in that very moment, but not as part of the way that the document is built.
I see. Yeah, so you said that like there are two main categories of 2D graphic editors. So the raster ones, which are like GIMP, which like, yeah, you decide your the size of your Canva, you paint pixel, and that's it. You get, like, if you zoom in, you will see pixel, and there are vector graphics editor such as Inkscape, where, let's say, you just define the shape of your image and you can zoom indefinitely. At least this is the way I think about it. And so you, in Graphite, you want to merge them, and the trick that, like, the how you do you plan to merge them is by using this node graph as node editor.
Yeah, exactly. So with vector editors, typically, because you're describing things as curves, not as pixels, you can actually zoom in and you will continue to render at this higher resolution. But that's never been the case with any other raster editors because they're always working on documents that are composed of pixels. And if you work at a certain resolution and then zoom in more, you don't have those additional pixels anymore. And what we're doing is we're kind of bringing that same concept that vector already benefits from, being what it's called resolution agnostic, where it doesn't actually care what the resolution is. It'll just render at whatever the resolution is that you're viewing it at. It's like in a game, if you are a 3D game, if you are looking at a wall from a distance, you can walk right up to that wall and keep getting closer and closer, and you're going to see it rendered for you bigger because it's taking up more of your screen. The same idea here. You can either render vector graphics by zooming in more and continue to get that resolution, or let's say you were drawing with a brush, and drawing with a brush is typically a raster operation. So if you're doing an actual digital painting, that is typically going to be something that commits your brush stroke, your mouse movement, or your, however you're actually drawing any stroke, to pixels. But we're not committing those to pixels. We're committing that as mouse positions into the node graph that stores the data of how your mouse moved. And then we're going to re-render whatever you drew at the resolution you're viewing it at. And let's say you zoom in a bunch, you're not even seeing the things that are off screen. So we're not going to bother rendering those things that are off screen at that moment. We're just going to render the pixels that you're seeing. And that's much more like a game where you are walking up close to a tree or something, and we're seeing the details of that tree. But if you instead go 2 miles away to another town in the game, you're not going to see that tree except as a few pixels covering up a little bit of your screen. So we don't render that in the detail that you need, but you can always go back and see it closer. But that's not ever been the way that that raster editors work. Typically, if you wanted to have a tree that was visible from the town over, if you're making a scene, you would have to have like a 1,000,000 by 1,000,000 pixel document, which is absolutely a massive file, it's going to be extremely difficult for your computer to keep up with that. You'd have to have an insane amount of memory. You'd have to have an insane amount of storage just to save that file. Whereas in our case, most of our documents are actually going to be very, very small. I typically work with Photoshop documents that can get up to like 20 gigabytes in size because I sometimes composite a large number of layers together that are also very large because they come off my camera. But in our case, we're going to store any kind of data you import. So if you actually import things from a camera, of course, we're going to just store those raw files as they are imported, but we use them more as data, and then we interpret them at runtime or whenever we're actually rendering the document. And of course, we'll have caching and things that are used to as part of that interpretation process. But when you actually save your file, any changes you make are really just going to be, a few kilobytes in size because we're just describing the operations that go on that you stacked up and you built this graph of operations rather than storing additional layers of millions of pixels, which actually takes a lot of data. So this allows us to be non-destructive, meaning you have more creative control later down the pipeline. After you've made creative decisions, you can go back and change them. But at the same time, we're also going to use less storage. Of course, that's the traditional thing in computer science is memory versus time. So we will, of course, use less memory, but use more time to compute things if you open up a document brand new. So we might also be storing some of these operations that are particularly expensive. We might store them cached into the document optionally and allow users to encode that into the document or not encode it into the document, but it'll take longer to open for the first time.
With cache, like you mean that you create snapshots of like after, I don't know, 1000 operations, you create a snapshot, and then when you load your project, it will start calculating the operations from this snapshot.
That's definitely one way to do it. Dennis, do you want to cover this one?
Yeah, so what we can do is that we still have the resolution agnosticism. So if you were to, one trivial way to do a snapshot is that we just render the document at some resolution and just treat that as a big pixel bitmap. But then, of course, if you zoom in, you once again see pixels, and we have to recompute that. But the graph is more complicated. We don't just have rest operations which need to be composited. We also have, for example, if we have some vector, as you know, we can mix both vector and raster workflows. So if we, for example, have a vector workflow, we can, this is a computer programming languages term, we can constant fold things that don't change. So if we have a big graph and there's one branch that just does nothing, it always stays constant, we can just pre-compute the branch and use the result. And we don't have to recalculate this entire branch of the graph every frame. We can cache it, and that's where our intelligent caching system will come in. And we also have some of that already in place, intelligent caching, where we don't always recompute, because that's a huge issue. As you mentioned, this is pretty similar to how a game engine operates. We also get the same issues as a game engine. A game engine has to deal with performance issues. Like we don't want the editor to lag if you zoom in. It should feel smooth and instant. You don't want your game to lag. It's the same problem, and we have to come up with the same solutions, basically.
Yeah, we're actually taking a lot of concepts from the game industry and the graphics pipeline that's typically used by games, and bringing these more to the world of traditional 2D graphics. Because if you think about it, Photoshop is something like 35 years old at this point that far predates any 3D games that were meaningfully graphically intensive at the time, using anything that resembles the modern graphics pipeline. And those concepts sort of carried forward into the entire world of 2D graphics. But nowadays, GPUs, graphics drivers, most of the graphics world in its development and its research has all focused more on rendering and on game development, because that is by far the biggest industrial component of graphics. So as a result, being able to tailor our approach towards being more compatible with those, both from a rendering perspective, as well as even just a conceptual perspective, where we're actually taking some of these just generally ideas, like the idea of resolution agnostic being equivalent to walking up to a tree in a world in a 3D game. These concepts, they're completely normal for graphics engineers that are working on 3D games. But bringing this to the world of 2D is actually sort of merging this with the ideas that have predated the 3D worlds from 2D graphics editing that has existed for 35 years.
I see. Yeah, I think that like you can do a lot of innovation by bringing ideas from another field into another one. And
Exactly. Yeah.
I don't know if I'm right, but like your process of optimizing the of caching the node graph, the node like the operations, it looked to me similar as the compiler optimizing assembly or like optimizing your code, removing an unused variable. Is it similar?
It's the exact same thing,
Okay.
and we're using
This
the same
gets into
techniques.
the core thesis, which is that our entire node graph is itself a programming language, and I'm very excited for Dennis to explain all that.
Nice.
Yeah, this is a doozy. So in Graphine, like Graphite is the project, and Graphine is our node editing language. And Graphine itself is a purely functional programming language. And every Graphene node is bijective, so it has a one-to-one mapping to a Rust function. So every node is implemented as a Rust function. So what we can do is that we have a bunch of nodes. The nodes are connected with other nodes, and we can then translate those nodes into their respective Rust functions and just make a call graph. So one node calls another node because it's connected into the node's input. We can translate that to one function calling another function. So this entire node system is just a functional programming language. But what we end up doing is, well, we have multiple versions of our basically compute runtime. There's an interpreted version where we at runtime do dynamic linking and dynamically link functions together, like small functions, which are nodes. We link them together to form one coherent graph execution.
I'd also like to quickly interrupt and explain what these nodes might be to give a more physical understanding.
Please do.
So a node could be one node, which is a Rust function, can be something that builds the data to render the pixels that show up on the screen for a brush stroke. So if you're drawing a squiggle with a brush, this will be a function that can return the color of each pixel that renders that brush stroke. Or another one could be something that takes input data of an image, and then it gives a blurred version of that image. Another one could be something that replaces all the colors with 50% opacity. So you take an image and then you kind of overlay any color of your choice on top of it. Or another one could be something that takes a vector shape. So this is something that's infinitely scalable because it's defined as mathematical curves. And it basically is a node that stores or produces something like a circle or something like a star or some arbitrary shape. All of these are the different types of data that combine together in different ways. And then we have things that might render from a shape into pixels. So when you're viewing a curve, you need to be able to go from the mathematical description of a curve and then give it color information so it knows what color it should be or how its gradient should look and how that gradient is aligned. And that will then produce pixels that show up on the output view. So these are all just some examples of how these Rust functions combine together, because you might want to draw something with a brush on top of an image and then composite those on top of each other by blending the top pixels to the bottom pixels, and then change the color and then blur it. All of these different things combine together into what ultimately produces your entire artwork.
Yeah. Also, one thing, like Keavon just mentioned, a bunch of nodes that take something as input and transform it, but actually the input is a node as well. If you insert an image into the node graph, that's also a node. It's a function that doesn't take any input and returns an image as output. So all of those are functions that we can translate the nodes to functions, and we can then use programming compiler techniques to do things like constant folding. So constant folding is you look at a branch of your program which doesn't change. It doesn't depend on any input. So you can just compute it at compile time and use the computed result. And that's one of the techniques that we can use. And as I mentioned, we have Rust functions. Another thing that we can do is that we actually just copy paste the source code for these together, or well, the function calls. And then we can let the Rust compiler compile the entire thing into a single binary. So we can let the compiler do all the optimization and inlining to actually produce an optimized binary. And we can also do that at a granular level. So for example, if we have some part of the node graph which doesn't really change that much, we can take that branch, like that section of the node graph, and compile it to a binary. Then we can seamlessly swap out the nodes for that precompiled binary, which is now optimized to even further improve runtime performance. And yes, it's very much a programming language, and I'm very excited about that.
Yeah, essentially it's one giant Rust program that renders your final artwork. And Graphite as a tool is a way of providing a user experience to that programming language to interactively modify your artwork and build artwork that is building a Rust program to render your final artwork. And it will interactively do that as you make changes. It will change that program, render it in real time for you to see. But then finally, that Rust program at the end of the day, when you're done with creating your artwork, that is a Rust program that produces your artwork. And it can produce it at any resolution you want. You can say, I want this to render at the size of a billboard, because you're going to go print a giant billboard that is going to be, like 40 meters across or something on the side of a highway. Or you might want something that's really small. Anything like that, any of these images that you're going to use, you can render it at any resolution you want, because it's ultimately a program that builds artwork. And Graphite is a program that allows you to interact with it and build that program that builds the artwork.
Okay, yeah, the fact that while you're editing an image, you're producing basically a Rust program or even a Rust binary, it's mind-blowing. And like
it's kind of like it's an IDE for Rust.
Yeah, it's incredible. Yes, and like it makes me think that like if people are looking to contribute to this project, maybe I don't know. The thing that I will think is, well, I'm not into graphics, but in reality, you can contribute. Like Graphite, I think it's a very big project, and so you can contribute to small areas that are not related to graphics. They're related to, I don't know, programming languages, compilers, and stuff like that. Yes,
especially programming languages and compilers. That is something where most of our existing contributors come from mostly a graphics background, but we do actually really need people more from a programming languages and compilers background, and also even more of a distributed systems background as well, because the other thing we didn't mention is that this language is also built to be as distributed as possible, so we can distribute resources across CPU, GPU, and even a cluster of machines on the cloud. So also distributed systems as it pertains to it's sort of like the intersection between programming languages and compilers and distributed systems. All of those are things that we actually really sort of have a lacking of expertise in. We have Dennis, but we don't really have other people that have that kind of background. So that's the kind of thing where it would be super valuable for us to have people who come from that background rather than a graphics background to join that team.
Great. So yeah, if you're looking for a project to contribute, definitely check out Graphite. And yeah, I would like to ask you, why did you pick Rust as a language to write Graphite in the first place?
Yeah, it seemed kind of obvious, but it definitely wasn't a trivial decision. I mean, it seemed obvious once I had done the research and concluded it. There was very obviously no other choice that would have made sense after I did the research. But some of the real reasons were, some of the driving reasons basically was I wanted something that could work in the web. And that was because I had spent my past, 13 years in education, or however many years that I was doing this, where I would remote desktop into my machine on the school's libraries. So I would download remote desktop software and then log back into my machine at home, so I could use Blender, so I could use Photoshop, so I could do any sorts of advanced things, because the software on those school computers and also just the processing power on those computers was not sufficient. But having a powerful program that's purely web-based, it doesn't have to be web-based, but it can be web-based for people who want it to be, who are just logging in from a school computer or just want to open up something quickly and do some small changes to an image on occasion. Those are cases where having that capability to be web-based is really important. So I really didn't want to compromise on having web, Windows, Mac, Linux, and also probably iPad in the future being our targets of choice. And the web ecosystem basically means, but the other thing is I wanted to make sure that the desktop versions could be actually native desktop, and they're not just going to be running inside of an Electron application or something. So having something where I could write native code with native performance and not have to write everything in JavaScript, which is just slow. Especially in the context of something that's very graphically intensive. That was something where there's not too many choices. You can do C and C++, which has, I guess, within Scriptum, you can do WebAssembly compilation, but the most ergonomic choice is Rust. And then you also have a bunch of other libraries that Rust provides that there really isn't too much of an equivalent of in C++, until recently, at least. I guess now there is Dawn, which is the C++ equivalent from the Chromium team for the WebGPU implementation. But basically, WebGPU is the replacement for WebGL. And that is a specification for using modern access to graphics cards that works on any platform. So typically if you're writing a desktop application, you're going to be using DirectX or Metal for Mac, or Vulkan or OpenGL for Linux and other platforms, and I guess also Windows, but mostly you'd be using DirectX on Windows. But the WebGPU standard is one that allows you to write JavaScript and make it run in the web browser, regardless of whether you're on Windows, Mac, Linux, or even mobile devices. But having the same that same standardization and interoperability, portability was the word I was looking for. Having that same portability for native programs basically means that you have to use what's called, in the Rust land, WGPU. That is a crate that allows you to write what is basically the Rust equivalent of those JavaScript calls for the WebGPU standard, because the WebGPU standard is the one that is a new browser API. But the Rust equivalent of those calls allows you to use WGPU, not WebGPU, but WGPU. That's the Rust crate. And that Rust crate allows you to then compile native applications for Windows, Mac, Linux, or web, using a backend of either Vulkan or DirectX or Metal. Those are the three different APIs for the three main operating systems, or the web, which is going to then compile to the WebGPU API, which is what Rust is ultimately wrapping for you. So that was a lot of words, a lot of very similar terminology here. But the important part is being able to either use C++ or Rust. So C++ would use something called Dawn, which is by the Chromium team, but that only came out very recently. And then WGPU came out, well, I guess slightly earlier, maybe at the same time, but it's the Rust. It's basically the preferred way within the Rust ecosystem to make portable graphics applications that run natively or on the web. So having that library really allowed us to pick basically either C++ or Rust as our main choice. And it's honestly just, Rust is a much nicer language. And then there are some additional reasons as well, but I can get into those a little bit later if you'd like.
Yeah, sure. So yeah, you choose Rust because of performance and like portability and libraries support. So WGPU lets you build you write your program using WGPU, and with WGPU you can target like Windows, Mac, Linux, and also a web browser.
Exactly.
Yeah.
Okay.
It will natively target those graphics APIs, allowing you to run both compute shaders as well as regular shaders, regular graphics pipeline shaders, to do rendering as well as computation that's distributed across thousands of cores that the GPU provides you. And that's very much needed for graphics applications such as this.
I see. But like, what's the interface that WGPU provides as a programmer. So I think that it doesn't provide like, I don't know, buttons or text inputs is lower level, right?
Well,
it's an API
yeah.
directly to call and run programs, distributed programs on the GPU, and you build those programs. And here's actually the cool part: is one other part of the Rust ecosystem that's something that you can't do with C++, is that thanks to Embark's project. Embark is a game studio in Stockholm, and they're building a project called RustGPU, and it is a compiler backend for the Rust compiler itself to write your shader programs in Rust so that they run on the GPU itself. And that allows us to reuse our code that runs on the CPU on the GPU in most cases.
Okay, so that makes Graphite faster because it runs on the GPU instead of the CPU.
Yes, and allows us to do that more easily. We don't have to spend as much time, therefore, porting the CPU code to the GPU for every single node that we write. It just happens in most cases automatically. There are some cases where we're doing something that's impossible on the GPU, but those are, and we might have to like have an alternate version for those ones. But most of the time, and you can even just use like, I believe, compiler flags to say compile this section of code for the CPU and this version for the GPU.
Yeah, so I'll have to interject there.
Yes, I think you can do a better job describing it than me.
Yeah, so what RustGPU actually does is it's a code gen backend for the Rust compiler, as Keavon said, and it targets SPIR-V. SPIR-V is a binary shader application format spearheaded by the Vulkan, by the Kronos group, and the implementers of Vulkan. For Vulkan, it's basically the Vulkan shader format. And Vulkan, similar to Metal and DirectX, are graphic APIs. And WGPU is basically a meta graphics API, which is a layer that translates into the different specific platform-specific APIs. It just translates the calls. So we can use one interface to access all of them. And as Keavon mentioned, we can use GPU acceleration inside of our node graph. And we do that through, well, for now, currently we do that manually. Like you can place nodes to, it's basically a map execute on GPU node, and you then can provide another node as a lambda to this node. And in Rust, you can, like in Rust, you have the .map function, which executes something for every value. And we have a map GPU function, which executes a lambda on the GPU, basically. And that's how we can encode the GPU execution inside of the node graph. And that actually touches on another neat thing that I forgot to mention earlier, and it's the goodest time as any to do that. Graphene really does provide somewhat of a paradigm shift, how we can think about what our node graph does. For example, if you wanted to implement something like batch processing for images, like you notice that your image sensor has a dead pixel, so there's a black spot on every image. What you could do is that you manually go through every image and use a repair tool to remove that black pixel. But what you would do in Graphite, well, in Photoshop, there's a specific batch processing function. The Photoshop developers build a thing for doing batch processing, which is its own thing. You can specify a folder and then it applies it to all images in that folder. But how you would do that in Graphene or in Graphite is that you do it for one image, and then you just use your node graph as a function. And then you use a node which loads all image names in a directory, and then you use the .map function, like the .map node, on this vector of image names, and then apply the image operation to all images, and then save all of them, like doing some sort of for each collect thing. And that's just a way how in Graphite, something like batch processing, it's a property of the node system that just naturally occurs. It's an emergent behavior That's one of the key design principles behind the Graphene language. I wanted to do as much as possible just from within the language itself. It's not the runtime. Like that's similar to like the design paradigm shift between, well, design differences between something like Rust and C. And in some sense, Graphene is more similar to a C-like programming language because most of the functionality is not provided by the runtime. It's actually built from within the language. Like you combine constructs in Graphene to build more complex things. For example, like batch processing, that's all just an emergent property system. We didn't do anything to implement GPU code like in the runtime. You can just write a node and the users can write a node. That's the empowering thing. Graphene is about empowering users to do what they want. And my kind of, as the sort of chief designer of the Graphene language, my job is to get out of the user's way. If they want to implement something, they should be able to do that. And I'm trying my best to allow them to give them any freedom, flexibility they want so they can do whatever they want without even needing to change the Graphite source code.
And more tangibly, the way that works is that, yeah, within the editor, people can either combine together a large number of nodes into a single node, and that is a new function that does something that they built out of the emergent properties of other nodes that they used. Or they can even open a Rust text editor, write a Rust program, and then compile that while it's still in the editor, and that will become another node. So you have two choices. One is to build it from scratch with Rust source code, or the other is to generate it out of a bunch of nodes and combine them into a single node.
Okay, so if you want to do like this batch processing, you can define the operations that you want to do either by doing them with the UI or by writing a Rust program.
Yes, I mean, of course, you could also just write a Rust program that opens a directory and then does all the operations. But the main thing the point I was making with that argument is that we don't, as Graphite developers, we don't have to create a new menu, batch processing. We don't have to create a UI for batch processing because batch processing is already basically implemented. It's something that you can do yourself from within the language. And if there's ever a different, like we as Graphite developers don't have to implement batch processing, which decreases our burden on the things we have to do to reach feature parity. That's also a thing. Like if users need a feature, they can also just build the feature themselves. We don't have to do everything, which makes it a lot easier for us to reach basically a viable product, an MVP stage.
Yeah, so like, are you talking about plugins and stuff like that? So maybe people can define, I'm thinking like people can define maybe new tools by combining existing tools and creating a new combination of operations.
Sort of like that, yeah. We still have to figure out exactly how tools, which is like the paintbrush tool or the pen tool, those kinds of tools that interact with the document. We still have to figure out how we're going to do plugins for those. We do definitely want to support that in the future. But more generally, the ability to say, I want a very custom kind of blur that does some interesting graphical effect that looks sort of like blur, but different in a certain way. A user doesn't have to file a feature request and ask us to build it because they can just build it themselves, either by combining together other nodes or by writing the Rust code themselves to make that node that does that blur. Or they want to have the ability to batch process an entire folder of nodes, an entire folder of images. Or they want to ingest data from an API and convert that into a batch of images. So they grab data from a database, and for every row in that database, they export an image. We don't have to go and make a menu item that says, like load data from a database, blah, blah, blah. They can just go grab a node from our entire catalog of nodes and build that functionality to meet whatever their interesting and unique use case is. and that allows us to avoid feature creep. So we don't have to add millions of weird things to menus that most people are never going to use, and therefore it's going to be distracting that they have to go look through this giant list of menu items that are almost never going to be used. That is something that's quite bothersome to me when I'm using existing graphics editors that I use day to day. I only use maybe 10% of those menu items ever, because most of them are very, very niche and specific, and you're going to go your entire career without ever using the vast majority of them. And avoiding feature creep allows us to provide that functionality to only the people who need it by just grabbing a node from the node catalog.
Yeah. Another good example of when that can be used is if, for example, you want to make YouTube thumbnails, and let's say you do a series. If you were to upload this to YouTube, for example, you would add like the text, RustShip podcast, episode number, and the thumbnail, like our faces or something. And how you could do that is for this episode, you could just specify a CSV file in which you write like episode number, episode title, image to use. And then you can define a Graphine graph or a Graphite document, which loads the CSV file and then generates the thumbnail image for you. So that's another way how you can very easily automate everything you do. That's also an influence of having programmers also having their hands in the design and also.
I will look into that again.
Yeah. Another example that's similar to that one would be if you're building a trading card game and you need the artwork as well as the name of the card, what level the card is, what the elements are, like different tags, the lore description at the bottom, which class can use this card, all that different information that needs to be displayed on this card. But then you have 1,000 cards. So you're definitely gonna have to put in the effort to build the artwork, to draw the artwork for that card. But all the rest of it is just text, or it's metadata in the sense that it's like this elemental has this effect and it's this level. Those are all just like data, basically. If you can write in a spreadsheet all the columns for describing that card, and then one of those cells in the spreadsheet is a link to the image that you're using. So it could be either a URL on the web, somewhere on the web, or it could be a local file, or it could be from your FTP server, or it could be grabbing it from some private source like an S3 bucket or something. We'll have different ways of grabbing resources. And you basically just add a new row whenever you want to design a new card. You just add a new row to your spreadsheet, and then you just tell Graphine, or you build a Graphite document that is sort of the template for one card, and then you take that entire card example and feed it the title, like the text is from one cell or one column of the spreadsheet. The image is from the resource that's grabbed from the URL at another one, another column of your spreadsheet. And you basically make it so it takes the data from the spreadsheet and builds the card for you out of that template. And you can make a completely custom card without really any limitations whatsoever. And then you can blur the image if you wanted. Let's say you want like a vignette blur around the corners of your image. Then you can set it up to do that vignette blur. And you want to maybe change, basically you have full control, just like you're programming, over anything you would need to do. You can transform the text. Let's say you wanted to search for any word that uses the name of a character class in your trading card game. You can do like a regex search on that text and tell it to turn any of the text that has the name of that class, let's say with double square brackets or something, into something that becomes bold. Or it could even read it in like markdown format and then format that markdown into bold text or italic text or things like that. So you're basically doing like data processing on text form, on text before it then turns out as the formatting that goes into a text box that appears in your artwork. So you can basically have full control over the pipeline and make the stuff that supports thousands of cards. So you don't have to have a graphic designer going through and doing manual changes. And let's say you slightly modify your format. You don't have to go through and make that same change to your format 1,000 times across all your cards. You just re-export the 1,000 cards within a minute or so, however long it takes to render out all the cards.
Sounds great. Yes. Wow, it's very interesting. Nice. And yeah, I wanted to ask you. So Graphite runs both on like desktop and browser, and yeah, you said that WGPU made this easier. Like, I wanted to understand if, even if you use WGPU, if running on the browser still comes with some challenges with respect to the desktop version, and like, yeah, what are these challenges and how did you solve them?
Many challenges galore.
Yes. Yes. I can, like, from a, well, there are many challenges. For example, one of the things that is still that's still hard to do is, for example, multi-threading, as Keavon mentioned when we started. And also there is just there is a performance overhead of running in the browser. If we were to do the same thing natively, it would be easier. And there's also different browsers supporting different features. So for example, there were times where we had to disable Graphite basically for macOS and Safari users, because Safari just didn't support things that we needed, because those are just web API standards, but Safari chooses to not implement them. That's quite annoying. And yeah.
Supporting standards across all browsers when we're doing very complex things, not the things that a usual website's going to do, but the things that a complex, sophisticated web app needs to do that approaches the functionality of a desktop app. That's where you really run into the issue with being able to support things across all the browsers, because not all of them bother supporting some of these more complex APIs.
I see. So you would suggest to download Graphite locally if you can, instead of running from the browser?
In the future.
Yeah,
we don't actually have a desktop version maintained at the moment. We experimented with it, but we don't have any download available at the moment because we just haven't been able to put the maintenance effort into that yet.
Yeah, but that's probably going to change at some point because, well, we're currently using Tori, which is another Rust project, which is similar to Electron, but instead of using Electron, it uses the system native web view. And they've recently enabled the possibility to get a raw image handle. So one of the main issues is communication between the Rust code and the front-end code, which is still written in JavaScript, because it's basically just JSON string communication. And what we will soon be able to do is that for the native view, for the native desktop version, we can do the rendering purely in Rust and then basically inject the rendered viewport into the application and render the rest of the front end using JavaScript. So it's a kind of Frankenstein mix between having the UI run in JavaScript and the actual render viewport running in Rust. And at that point, the desktop version will become viable again and useful.
Yeah, to drive the point home, basically at the moment, we compile our Rust code into a WebAssembly binary that runs in the browser. And then there's some JavaScript that runs the way that you click on the buttons, everything pertaining to the actual HTML aspect of our UI. But then everything else, the actual core logic, all the rendering, all the business logic, all of the management of state, all of that happens in Rust within the WebAssembly binary, locally on your own browser. But all of that code, which is by far the most performance intensive part, the actual JavaScript itself is extremely fast. And people have commented constantly to us that, wow, this really feels like a desktop app, not a web app. It's so fast. There's just no latency when I click on buttons. I didn't know the web could be this fast. But all of that code is the code that's just really, really lightweight JavaScript that enables you to click on buttons and things. But all the other business logic of the editor runs in WebAssembly on the browser. But we can then, using the Tari architecture, using Tari as our desktop wrapper almost, all of the Rust code that we write, instead of compiling that to WebAssembly, which is a little slower because it has to be interpreted by the virtual machine that interprets WebAssembly. Instead, we run that natively on the Windows, Mac, or Linux platform as native code. And that's what Tari allows us to do, is compile that code natively and then still use the Tari API to communicate to the JavaScript, and the JavaScript will make changes to the web page and allow you to update update the UI, click on buttons, and just run the slight amount of JavaScript that's needed for that. I think about 10% of our code is JavaScript, 10 or 20% or something.
And have you considered like using Rust with WebAssembly also for the front end, so replacing this JavaScript with Rust in WebAssembly? I don't know if it's possible.
Eventually, we'd like to get rid of all of our entire JavaScript backend completely, but we are waiting on some long-term future projects, such as Xylem, which is the line bender slash Rafe Levine project that's working on kind of hopefully the final form UI of the Rust ecosystem once that comes online in the future.
Okay, so you're waiting for other UI libraries to come
Yeah.
to go.
It's probably going to be several years at a minimum before that is mature enough to be usable, and then we'd still have to wait to schedule that in our own roadmap to replace all of our front end that's written in JavaScript at the moment, which is very lightweight and generally works quite well, but we would love to make that even more native in the future by rewriting that into the Rust-based approach.
And why are you waiting for? Sorry, go, Dennis.
Yeah, we don't want to repeat the GIMP issue where GIMP noticed that there wasn't a great UI framework available, so they made GTK, and now there's GTK, and they spent a whole bunch of resources on actually creating GTK to make an image editor. And
I didn't realize that GIMP were the creators of that.
And the funniest thing is that now GTK is like, GTK is now at version 4, and for quite a while, like it's being replaced by now, but for the most time, GIMP was still on GTK 2, because they just never updated it. So much work. But yeah, we don't want to do that because that's a bunch of work, and we have enough on our hands with just implementing Graphite. So
our roadmap is insane.
Yeah,
it's
we're
just
using
mind-boggling how much work lies ahead of
resistance for now.
Yeah,
sorry,
most of the things that lie ahead of us are really, really interesting engineering problems, like version management. We're basically going to be building our own Git implementation to manage the file versioning. We have to deal with CRDTs to be able to make changes that sync automatically across different node graphs that have been changed by different users that haven't been connected over the internet. We want to support the real-time communication, able to make it so you can do collaborative editing, just sort of like Google Docs, where you both work on the same document at the same time. But even if one of you goes offline, we can then sync those back up afterwards without any kind of conflicts. That's just a tiny, tiny little glimpse at some of these things that lie on the future with our roadmap that are exciting engineering problems, but they are also quite daunting.
I wanted to ask you, why are you waiting for this particular Rust library, and why is it different with respect to the other available?
Because our UI is already pretty good, and we're quite happy with it. But we would like to eventually, as its final form, adopt what is perfection, essentially. And we think that Xylem is most likely going to be the perfect Rust UI library, but it's just going to take several years before.
Yeah, but I mean, if something better comes up, we're not that set on Xylem. It's just what currently looks promising.
Yes.
But it's also very much a research project. They might just abandon it. And
exactly.
There are also other Rust UI libraries. For example, the Cosmic Desktop team uses Iced as the UI system. So that's probably going to get a lot more mature for the next little while. So that might be worth revisiting at some point. But yeah, it's just this whole ecosystem is still in flux, and right now we're pretty. It does work pretty well with the browser, and it looks consistent across different operating systems. That's
yeah, absolutely. Like if what you have is working well, it's you should replace it soon. I think you have most important things to do. I just wanted to understand why you think that that this particular library is perfect, or is going to be perfect. Why do you think that it's better than the other one, to your liking, of course?
Yeah, I mean, ultimately, this point is sort of speculation on the success of different research endeavors that will go into building what Xylem hopes to be. But the main things would be the focus on utmost performance as well as ergonomics for developer experience of using the library. Another is the accessibility integration to be able to integrate, I think it's called Access Kit, to make it highly accessible. And generally, also using the rendering backend of something called Velo, which is the other project by the Linebender / Rafe Levine person / organization that is working on both the render engine as well as the UI framework. And we are using Velo. We shortly will be using Velo for our vector graphics rendering. So being able to render the UI with the same code base that renders our vector graphics is a good way of ensuring both consistency as well as reducing the binary size and keeping things lightweight and keeping things ergonomic.
I see. Thank you.
Yeah.
I wanted to ask you, like, I'm very curious about the collaborative editing part. And yeah, I wanted to ask you if you have, so it's not implemented yet, right?
Not at the moment. We had some small prototype with it a long time ago, but it was just a proof of concept.
It's basically how the infrastructure and the system design works, is that we have our JavaScript frontend and we have the Rust backend, and they communicate through message passing. So at some point, I just hooked up a small server, which just the JavaScript events were sent to the Rust backend, and the Rust backend then echoed those JavaScript messages to a WebSocket connection, and then to a server. The server broadcasted it to all connected clients. That way, we basically just replicated user inputs across both browsers, and that allowed us to edit the documents in sync. That was quite a useful experience to have. I implemented that in like a day or half a day. But for that to be more robust, we need the CRDT-based Git-like approach, and that will still require a bit more research. And that's actually that's a topic in academia that's not even fully solved yet. So we will probably have to publish a paper on that once we come up with a good solution. And I'm pretty confident that the solution I've come up with is already pretty good. So we'll have to see.
Yeah,
nice.
This is also a good opportunity for anyone who's interested in that research arm, especially of CRDT technology, to get involved and potentially co-author a paper or something.
Really interesting. And so Graphite, right now, it's all client-based, right? It runs on the browser. So you don't have an infrastructure where you're hosting something, right?
At the moment, the extent of our infrastructure is a couple proxies for different APIs that allow us to deliver you fonts from the Google Fonts API. And I think that is our only endpoint at the moment.
Yeah.
Okay.
Yeah, for now, that's also pretty good, because we will never run into a problem, because everything is executed locally, we will never run into a problem where we have a huge influx of users and we then either can't support that many users, or our costs just skyrocket, because it's an open source project. We don't charge anything. It's all free. So it's that could potentially kill the project. So it's pretty good that we don't have that issue right now.
Yeah, we want things running locally. And that can also get into a little preview of our longer term way of supporting the project, which is that because the computation in some cases can be very heavy, and because we're building this to be very distributed, we will allow people in the future, if they want to speed up some really complex documents they're working on, they could rent cloud machines that help do some of the computation by streaming a description of the problem to the machine, and then it will send back the computed result over the internet. So people who want to subscribe to that, if they're doing complex, heavy document work, then we can do some of that rendering. And a good example of that is a lot of AI workloads. So if you want to do image generation with Stable Diffusion, and this is going to be our first use case we're really going to try and build out infrastructure for, is if you want to generate an image that can take several seconds. So you send out just something as simple as a description of the text that you want generated, and maybe a seed and any other kind of metadata that goes along with it. And that is just a kilobyte or something or less of data. And then we send back from the cloud machine, from the API endpoint, the rendered image much, much faster than it would have taken for your comparatively under-spec'd machine that's also busy working on other parts of your render. So basically, it's going to be basically rendering as a service for people who want to support the project by ultimately speeding up their own workflow. But that's, of course, always going to be optional, and we're not going to feature gate anything.
Yeah, and that's also where that might make sense for production studios with big graphics pipelines. If you think, for example, like Disney, if they were to use Graphite, then they would have of course, a lot bigger, they have requirements which normal users don't have. So in that case, it might make sense to provide them with extra compute power. That's another potential revenue source.
We want to, of course, make everything run as fast as possible, but sometimes you just need to throw more horsepower with more machines at it. You might need 100 GPUs instead of one GPU.
Okay, so yeah, one idea for the business model is to that people from their laptops can experience a faster Graphite because it runs on your server, right?
Yeah, and in the future, once we build that infrastructure. Of course, we are not infrastructure people. That is one significant hole in our experience as a team, is that we do lack any of that infrastructure. So if anyone is very good in infrastructure and wants to help out with the project, that would be fantastic to have someone with some kind of both a machine learning background as well as a infrastructure kind of background. Both of those would be tremendously valuable, because we do have to build out an account system and a way of spinning up and spinning down different machines that can do both Rust compilation, because we need to compile people's Rust programs, as well as machine learning distributions where we can generate images for people, or do large language models that could be customized. If for example, you want to ingest a spreadsheet of data and then get a large language model to convert that data into paragraphs that then gets put into whatever sort of template-based thing you're doing. If you want to make 100 different templates, or you want to have a business card for your 100 employees, and you want to take their job description and have the large language model convert their job description into a 1 or 2 sentence bio or something like that. Those are all examples where we want to have the ability to have nodes that are kind of wrappers for machine learning models that you could even customize or train on your own, and then execute those, where it might just be you might not have a graphics card with enough VRAM locally. So you actually have to just do that on the cloud, because you just might not have the machine that's needed.
Okay, so basically I can provide both, I can provide both the pipeline of the operations that I want somehow, and you can also generate the image, because if I go to, I don't know, DALL-E and this kind of image generation, they only generate the final image. But instead, if I use the AI from Graphite, first of all, you provide me with the Graphite project so that I can more easily add the image after, I guess, right?
So the experience should be seamless to the user. The user shouldn't notice a difference if the calculation is actually executed on a different machine or if it's executed locally. That shouldn't make a difference from the user's perspective. It should just be faster.
Just speed would be the only difference, hopefully.
I see.
Or in some cases, the inability to run locally, because you might actually not have enough VRAM that's necessary for a certain machine learning model. So we might just have to throw an error because it's just impossible.
And you mentioned that you want to use Stable Diffusion. I wanted to ask why you picked this technology instead of the other ones, such as DALL-E, what's the other one, Midjourney, and so on?
Yeah, Midjourney doesn't have an API, I think Dolly does, but it's proprietary, so you can't run that locally. And we really want to be able to allow people to run things locally. So Stable Diffusion is the open source one, and that allows you to run it locally. And that allows us to control the infrastructure because we can't really deploy it ourselves if it's not open source and we don't have access to the project, to the code. So Stable Diffusion is the one that allows people to run it locally as well as us running it. But again, we don't really have infrastructure experience, so we have not figured out how to cost effectively scale up and down the necessary machines that are able to run different instances. Keeping in mind that because they require so much VRAM, it can actually take several minutes to load a model into memory. And that is quite slow if you need to have one user log in all of a sudden, or maybe there's 5 users all of a sudden, and they all decide to come and use the project. Then you got to have a few minutes dedicated to spinning up another cloud machine. And then they cost something like 30 or 40 cents per minute to run, or per hour to run. And then you need to scale them back down as soon as you're done using them, but you don't know precisely when the user is done using them. So it's all a bunch of infrastructure challenges. And we might start out early on just using an API from another provider and maybe allowing people to just either use it for free at a small scale or pay enough to support both their own usage plus the usage of the free users. We, at the moment, are not really trying to make money from it as much as just being able to financially support providing it to users for free. Where if people want to use it enough that they're really costing us money, then they're going to have to pay a little money to chip into the pot. But ultimately something that can start paying both me, because I am working full-time on this project, and turning down the opportunity to get paid hundreds of thousands of dollars a year working in Silicon Valley, which is where I live, or also being able to, in the future, once Dennis is done with his career, with his college career, to then start with Graphite full-time as well. That is our goal over the next year or two, is to start building a business model that allows us to continue with this full-time and make it sustainable, because that's the other big thing about open source projects, is that they frequently just sputter out when the maintainer gets bored or isn't interested in the very long-term commitment. And we really need to make sure that this is a long-term thing.
That makes sense, yes. And yeah, for now, like if you like Graphite, you can donate to the project to support its development and so on, because yes, it's all free and open source.
Yeah, great. On our website, which is graphite.rs, RS for Rust. Graphite.rs is, we do have a donation page there.
This video was extracted from the RustShip podcast. You can find the full episode on Spotify, Apple Podcasts, or your favorite podcast client. If you liked this video and you want to learn more about Rust, subscribe to the YouTube channel and follow me on LinkedIn, X, and Mastodon. You can also share it with your colleagues if you think they would like it. Bye!